Hi people, this video is on end behaviors and discontinuity, and we're just going to do some practice questions after an exploration that we have done in class. So in the first part of this video, it says for each of the functions below, determine any vertical asymptotes and or holes in the graph. So this right here, these two things right here are discontinuity. And before we do anything at all, we want to always factor. Having everything in factored form is going to help us to have a better understanding of what's happening here. So let's take a look at our first example. So our first example is given as f of x. I'm going to try to see if I can factor this first function. Well, my numerator right here is x minus 2. There is nothing that I can factor out. There's no common factor. There's no difference of squares. It's not cubes. It's only two terms, so it's nothing else. So I can't factor the numerator, but in the denominator, I do have a trinomial that I can factor. And when I factor it, I get x minus 4 times x plus 1. Well, remember, you are not allowed to have 0 in the denominator. We can't divide by 0. So what that means is we have some restrictions here. We're saying that x cannot equal 4, because if I put 4 in right here, I just set each part equal to 0, right? So I set x minus 4 equal to 0 and x plus 1 equal to 0. And in doing that, I figured out that x cannot be 4, and x can also not be negative 1. So now the question is, do we have vertical asymptotes or do we have holes? Well, remember, holes only happen if we have a function that behaves like a different function but is undefined at a certain point. But this function right here does not behave like anything else because we cannot simplify it. Again, because you cannot simplify this function, it doesn't behave like anything else. So because of that, that means that we have two vertical asymptotes. The first one is at x equals negative 1, and the second one is at x equals 4. And we're all done with this type of a question. Well, in the next example, it's a very similar idea here, but I want to factor as well. So f of x right here is going to be equal to, now in the numerator, that's a difference of squares. So I can factor it as x plus 5 times x minus 5. And then I can look at the denominator, and there's nothing I can factor with that. So I'm just going to write down x plus 5. Now, this x plus 5 and this x plus 5 divide out. So we're going to say that f of x behaves like g of x, which is the simplified version of f of x, which would just be x minus 5. But because in f of x, we have that x cannot equal negative 5, then we also have to specify that x cannot equal negative 5 in g of x. It has nothing to do with this, even though it looks like it might have something to do with it. But it's not to do with this x minus 5. It's because right here, when I set x plus 5 equal to 0, I get x equals negative 5. So because it behaves like this function right here has no vertical asymptotes, which means that we have a hole at x equals negative 5. But we have to write this out as a coordinate. So how do we find out what the coordinate is going to be? Well, we know the x value is negative 5, but to find the y value, we plug in negative 5 into g of x. We cannot plug this into f of x because if I do, then I would get an undefined value, which happens because we have a hole there, right? But at g of x, we can say that it would be negative 5 right here, and then I would have a minus 5, so it would be negative 10. So that means that we have a hole at negative 5, negative 10 with no vertical asymptotes because our g of x function does not have any vertical asymptotes. So just a reminder that vertical asymptotes or holes in the graph have to do with discontinuity. We're looking at things happening within the graph. In the next set of questions, it asks us to identify the horizontal or oblique asymptotes of each function. Well, our horizontal or oblique asymptotes now is referring to end behaviors. How do my graphs look on the ends of our graph? For large values of x in the positive direction as well as in the negative direction. So this time I don't need to factor. Factoring is not necessarily going to be helpful to me. So there's two different ways that we can look at it. So for one way to look at it is, if we're talking about really, really, really large values of x, then we're talking about as x approaches infinity. So we're finding as x approaches infinity of this entire function. So I'm going to rewrite this whole thing down. Now, we're talking about super large values of x. So if I take like 1 billion and I square it, it's going to be a really big number. Compare that to 4 times 1 billion. It's not, this 4 times 1 billion doesn't really matter. So right here, and this minus 21 doesn't matter at all. It's like chump change. It doesn't mean anything at all when we're talking about super, super large values of x. So this means that this limit right here is approaching x squared over x squared. Like this stuff doesn't matter for large values of x. It's too small to compare to this x squared. This minus x minus 20 is just way too small to compare to this x squared right here. So then right here, x squared over x squared reduces to 1. So that means that my horizontal asymptote is going to be y equals 1. But you have another option, and your other option is to do long division. So method number 2 is going to be to do long division. So I'm dividing x squared plus 4x minus 21 by x squared minus x minus 20. So right here, when I do this division right here, x squared divides into x squared 1 time. So I'm going to put a 1 right here, then I'm going to multiply it through. So I get x squared minus x minus 20. So then when I do my subtraction of all of this stuff, x squared minus x squared subtracts out. 4x minus negative x is positive 5x. And negative 21 plus 20 becomes becomes negative 1. Well, again, when we are talking about super, super large values of x, this stuff right here doesn't matter. But for starters, can I do any more long division here? No, because I can't divide 5x by x squared right here. So in the long run, this remainder, it doesn't matter. 5x minus 1 doesn't mean anything when we're talking about super large values of x. So right here, this would be the equation of my horizontal asymptote, which would be y equals 1. Also, we know that the horizontal asymptote that we have here is going to be y equals some constant because the degree of the numerator and the degree of the denominator are the same as each other. So now I'm just going to take a look at my coefficients, and 1 divided by 1 would be 1. Okay. In the next example, we're going to look at it both ways again. So in our first method right here, we're going to look at the limit as x approaches infinity. So here, it's going to be the limit of 2 over 4x squared plus 10x minus 6. So right here, when we look at this right here, 2 means nothing when we're squaring huge numbers right here. Okay, 10x means nothing. This minus 6 means nothing. But even though the 2 means nothing, I'm still going to put it there just kind of as a placeholder. So we get 2 over 4x squared. This stuff right here doesn't matter. So then I end up getting 1 over 2x squared. And here I'm taking 1 and dividing it by super, super duper large numbers. And when I do that, that means that this right here is going to be approaching 0. So that means that the equation is y equals 0. But we also know it's going to be y equals 0 because the degree of the denominator is larger than the degree of the numerator. Okay, and then our second method is we can, again, just do long division. So here's method 2. And here I'm going to take 4x squared plus 10x minus 6, and I'm going to divide that into 2. Well, 4x squared cannot go into 2, so it's going to go in 0 times. So that's why my horizontal asymptote would be y equals 0. Okay, so now in this last example, this time the degree of the numerator is 1 more than the degree of the denominator. So because the degree of the numerator is equal to the degree of the denominator plus 1, we will have an oblique or a slant asymptote. Well, if we have an oblique or a slant asymptote, that means that we are going to have the equation of a line. It's going to be in the format y equals mx plus b. So right here, to find this, we only have one option, and our one option is long division. So I'm going to take x minus 1, and I'm going to divide that into 2x squared plus 3. Don't forget to leave that 0x there as a placeholder, or you just can leave space there, okay? So now I'm going to look and see, well, how many, what would I get when I divide 2x squared by x? And we know that that would be 2x. So 2x times x is 2x squared. Just distribute it through. 2x times negative 1 is negative 2x. So then I'm going to subtract that through. The 2x squared subtract out, and then 0 minus negative 2x is positive 2x, and then bring down the 3. And then I'm going to do the same thing. Sorry, people, this 2x right here should have been on top of the 0x. So this right here would be 2x. So now I'm going to look and see, well, what is 2x divided by x? And that will be 2. So right here I'll have plus 2. Distribute this 2 through. I end up getting 2x minus 2. Subtract that out. The 2x minus 2x subtracts out to give me 0. 3 minus negative 2 is positive 5. This is my remainder. My remainder doesn't matter for super large values of x. It means right here that our graph is approaching the line y equals 2x plus 2. So here we're going to say y equals 2x plus 2, and that is the equation of my oblique or slant asymptote. Just a heads up, in the other two examples that we just did, these are going to be horizontal asymptotes because they are horizontal lines, right? The slope is 0, so they just go straight across. Okay, let's verify these using Desmos. So as you can see here in this example, we have y equals 1 is going to be our horizontal asymptote. Even though something I want to bring your attention to is that the graph right here still, like this equation y equals 1 will still intersect the graph at in the middle of our graph. But remember, horizontal asymptotes are end behaviors. That's what we're talking about. And if you see right here, the graph is trying really hard to get closer and closer to y equals 1, but it just won't touch it. Here is the second example where it's clear that this graph is getting closer and closer to 0 in both directions right here. So right here, we're going to say y equals 0, not 1, y equals 0, and we can see that our graph is getting closer and closer to 0. And then here's our last graph right here where we can actually see that it's obviously not leveling off to a horizontal line. So I'm going to type in the equation of the oblique asymptote or the slant asymptote that we got. And as you can tell, our graph is trying really hard to get closer and closer to that y equals 2x plus 2, but it just can't touch it. But as you notice right here, it looks like it would touch it. But if I were to like zoom in, we can see that it doesn't actually touch it. Okay? And that's it for this video. If you have any questions, let me know. Otherwise, I'll see you in class. Bye.